All right, so we left it yesterday with a gap program, and now if I copy this code, because I did fix the errors after the video, and if I copy this code and I open gap, and actually let me quit this process. It's I'm still not used to the interface, but okay. So here we go. If I copy these. What? Wait. Oh, I think there's still some errors, but okay, it says number of conjugacy classes 20. So let's see if we can fix those things. So first, let's see if we can fix these. Because essentially that means that it's then done. And okay. Already that fast. So gap. Can I just do this? Yes. Okay. So it's got okay. So it's got these things here. Now let me see one thing. 1, 2, 3, 4. Yeah, the size doesn't matter. Now, what I guess this is napper bound, I guess. Okay, I still got these. And now I think what I have to do is I have to basically go back here and okay, so now we have representations of G. Okay, so now we have the conjugacy classes, which in the case we have the conjugacy classes. Exactly. So let me copy this, put it back in gap. Let's go with a new process. That's weird. What? That's weird. That's very weird. Now what I want to do is I want to go from these number of classes to now how do we go from these number of conjugacy classes to saying okay anyway, to say how can we find out now the conjugacy classes if the field were to have characteristic 2? Quit. Can I start a new process? Yeah. Okay, now it's working well. All right. So we have these classes. Now, all right. We have, okay, so we have this code. Can you rephrase what it's doing? I don't know if that helps with the so compute all conjugacy classes of G. Now, now let's say these. Okay, so now we have discontinuous classes. Now let's say I am looking for reps or iReps of G over a field of char 0. Is it okay to say that there are 20? Let's get this out of the code. What I'm trying to get at is yes, it's perfect. Okay to say that by the fundamental theorem of representation theory for finite groups, the number of iReps equals the number of conjugacy classes of G. Since the gap code you provided computes the outputs exactly 20 classes, then if you like an extended gap code to compute for all the full Carter table using Carter table and rate actions to release the degrees and other details of the. Let's do this. So again, I like that. I like that I can jump on. Okay, so how do I? Can you define Carter in this sense? And yes, please extend the code to give me the such table. Threads make it actually very, very easy. Threads make it very easy. Is a class function associated to the representation. The trace of the matrix representing G under this representation. Why is the trace of the matrix being used? Okay, so let's run gap. Errors. So, great question. This isn't arbitrary. It's a deliberate choice rooted in both mathematical elegance and historical development. Let me break down this. So, conjugation invariance. Meaning two representations are equivalent if there's an invertible matrix. Yeah, okay. The trace is invariant under similarity transformations because of the eigenvalues. Those diagonal sums don't change. Okay, so it's basically because it's a unique way to represent that. Okay. Carter's multiplicative, which is crucial for decomposing representations into irreducibles via the inner product with the multiplicity of an okay. The dimension, degree of the representation, the values, okay. Because of the Carter essential nature of the representation and the conjugation, which must okay. Yeah, makes sense. The code is broken though, and actually I can continue in the main thread. That's nice. In the meantime, how can we go from the 20 conj classes to the number of irreps we would have if we look at irreps of G over a field of char 2. I understand there is some module thingy attached to this. So how do we go from char 0 to char 2, and how do we compute the irreps from the conj classes? In the meantime, we're gonna copy the code. Oh, that's nice, because actually you can have the thread and this going on here. I like it. I like it. I like it. Quid. Really? So 1, 2, 3. Yes. No. Okay. Weird. Here. All right. From ordinary conjugate classes to can I ask you to read that?
From ordinary conjugacy classes to modular irreps in characteristic 2, you're spot on that the module thingy here refers to module representation theory, specifically representations of the group algebra, kg over a field, k of characteristic, p of 2, where k could be Uribe f2 or an algebraically closed field, like the algebraic closure of Uribe f2. In characteristic 0, xz over Uribe fc, the number of irreducible representations, irreps, equals the number of conjugacy classes, 20 in your case for G. But in characteristic P, things change because the characteristic divides the group order, where Moscow equals 108 times 2 times 2 times 3 times 3, leading to modular representations, where the simple modules, irreps, are counted differently. I'll explain how to transition from char 0 to char 2, how conjugacy classes factor in, and how to compute the irreps step by step. This is based on standard results in modular representation theory, EGZ from Isaac's character theory of finite groups, or the GAP manual. Since your GAP code already gives you the 20 ordinary conjugacy classes, we can leverage that directly to find the modular count. Step 1. Key difference between char 0 and char p. Char 0, ordinary representations. Irreps are a 1-1 correspondence with all conjugacy classes via the character table. The characters are class functions on the full set of classes. Char p, modular Brouwer representations. Representations are over the group algebra, KG, where K has char p, and simple modules correspond to irreducible Brouwer characters. Brouwer characters are defined only on p-regular elements, those whose order is coprime to p, i.e., not divisible by p. The number of irreps equals the number of p-regular conjugacy classes, a subset of the ordinary conjugacy classes. Why p-regular? In char p, elements of order divisible by p act nilpotently and...
Yeah, wait. So the number of irreps equals to the number of p-regular conjugacy classes. Okay. Brouwer characters are defined only on p-regular elements, those whose order is coprime to p. P being, I guess, the character. Interesting. Not divisible by p. The number of irreps equals the number of p-regular conjugacy classes. Why p-regular? In char p. In char p, elements of order divisible by p act as nilpotently in some sense. Just give me a second. All right. Nilpotently in some sense. Their minimal polynomials have factors like SP, so they don't distinguish irreps as sharply. The theory collapses to focus on p-regular elements. Somehow it, in a blurry way, makes sense. But it says here for G, let's see, let's continue.
Some sense. Their minimal polynomials have factors like xpp, so they don't distinguish irreps as sharply. The theory collapses to focus on p-regular elements. For your G, order divisible by 2, p of 2, so p-regular elements are those of odd order, 1, 3, 9, or 27, since the 3 part is 3, 3. Elements of even order, involving the 2 silo subgroup, D can conc C2 times C2, and ignored for counting irreps. Step 2, how to go from the 20 ordinary classes to the number in chart 2. Identify p-regular classes. From your 20 conjugacy classes, count how many consist entirely of p-regular elements. A class is p-regular if its representative has order coprime to p. In your GAP code, the classes are computed via cc.fh, conjunction times conjugacy classes G. For each class, C equals in CC. Check the order of its representative. Order, representative C. Count those where the order is odd, not divisible by 2. The number of such classes equals number of irreps in chart 2. Why a subset? The p-regular classes form the p-regular part of the character table.
Would it be that
the
easy?
full ordinary table, 20 rows, columns, projects onto this smaller Brouwer table. Say k times k, where k less than 20.
Once you have the p-regular classes, computing the full set of irreps. Count the number. Two regular classes. Okay. Copy. I mean, the chart table thing. That's fine. I guess we'll start another thread in here. Can I close this thread and start this one? Okay, I cannot. Okay, cool. Would it really be this easy? I wouldn't be happy yet though, because I haven't fully understood that, but okay, let's give it a try. Let's give it a try. Oh, add this to the code. Sorry, guys. Can you add the code yourself? Can you add the code yourself to the code I already generated? I'm so lazy. But I could easily go back to these to say okay. Let's see. Let's see if that works. So I'm getting these. That'll be pretty dope, actually. So here, step 1, key differences. Step 2, how to go from the 20 to the number in chart 2. A class is P regular if its representative has order coprime to P. Okay. What does it mean? What? Wait. Bro, why 11? Why 11? It's funny because 11 is the number that Grok gives me if I just ask it. Hmm. Why is it doing... Why is it doing it like this, though? Why are we building the Broward table like this? 11 is a number that is it gives me if I just ask the question, and I know this is wrong. The answer is 5. Why? Why is it doing it like that then? Why can't we just use G? I don't know. But okay, I think maybe the problem is somewhere along these lines. But it's good having this code as a base. I think I might actually just work from there, because I think I more or less get the process of how you get, more or less. Okay, I don't fully understand that thing with the co-prime thing now with the Brouwer table, but that's something for the next session, I guess. But it's that's something to work from. Baby's crying, so I need to go, guys. I'll try one last thing. If baby holds, hold baby, hold baby, hold baby. Yeah, well, I'm not gonna be able to change that easy. I know. Okay, curse is grade G. Oh no, it's actually doing G. It's actually doing Brouwer table G. So why does it do these? Wait, did I copy paste the right thing? G. Okay, maybe it's just constructing G wrongly. G is not these. Maybe that's the problem. I'll ask it one more thing. I'll do one thing. I'm gonna ask Grok. I'm gonna stop the video now. I'm gonna ask Grok. Write the gap code to solve this problem. See what it does. Okay, I'm gonna try that just for fun. Okay, but okay, we need to understand. I want to understand the call thing, the call prime thing with P, and how you go from chart 0 to chart 2. But at least I have more or less a complete skeleton of like what the process is, right? So we're looking at the conjugacy classes, but then the process to go from the chart 0 to chart 2, I don't fully understand it completely. So I'm gonna feed the baby. See you next time.